Alright, I'm the third one in a row to present what we do with OpenFOAM. My name is Pieter Reyniers. I'm part of the Laboratory for Chemical Technology of Ghent University, and I'm here with a couple of my colleagues, being Jens, Laurien, and Stan, to present the work that we are doing in OpenFOAM, with a particular emphasis on how we use Tier 1 to do our OpenFOAM simulation. I'm focusing less on the application side and a bit more on the computational aspects and a bit of best practices on OpenFOAM. And I'm hoping to fill the next half an hour with that. To give you a first introduction to what we do, this is the way the head of the department likes to present our work, to emphasize the multi-scale approach that we use. So we are chemical engineers, so we have people doing very small detailed work. This is on the range of 10 to the minus 10 meters, so angstrom level. They optimize, or they do the optimal configuration of molecules with respect to each other, molecules and solids and everything. So this is very detailed work on catalysis. Then in between you have the chemical kinetics. So if you have molecules interacting with each other, you can describe global kinetics. If you put it in together, heat it up, pressurize it, what comes out. That's what we do in that part. Those simulations are, I call them lower level, because you can run them on your laptop, so we don't use heavy computational resources for them. But the model complexity is still there. You have to have the information on the kinetics. So that's their challenge. It's more on the chemical part rather than the computational part. And then the thing that I will focus on in this presentation is the top of the pyramid, so the process part, and then in this case the transport phenomena. This is again run using more intense computational resources, in this case CFD. But this was to emphasize that you can use HPC not only to simulate really big things, but also the small things sometimes need a lot of computational resources. The process, I want to dedicate one slide to that as well. It's called steam cracking. It's actually one of the most important chemical processes. It's done on about 100 million tons per year is produced of the one single molecule there on top. It's ethylene. That's a basic. It's a compound that is used to make polyethylene. Also, the other one is polypropylene. So there's a lot of plastics, a lot of consumer goods that are made based on these resources. And actually, how they're made, you have a hydrocarbon feedstock, being it crude oil, natural gas, or even now bio-based feeds. And you expose them to high temperatures for a short amount of time in order to break their hydrocarbon backbone and introduce these unsaturated. So you see in the molecules on top, you have these two connections between the black spheres. That's a double bond, and that's a functionality. So that's something that you can use to connect these molecules to each other and form a longer bond in a controlled way, which is then moldable into plastic goods. But the part that we will focus on, you can see in the two pictures there, is these long reactors, so these tubular reactors that are suspended in natural gas furnaces. It's a process both outside, so in the furnace, and what happens inside this reactor tube. That's what we are describing. Schematics, so you have the red line, it's the feed that comes in, is preheated in the top part and then passes through this loop, which is indicated as radiant section, and then is cooled down again, goes out. And what we have on the other side is the fuel, so the natural gas. The process is endothermic, it requires heat to be within. So in the furnace, a lot of natural gas is combusted to generate the heat to drive the chemical reactions to actually break the bonds. One of the downsides of this process is called coke formation. I have to introduce you to this because this is what we want to prevent with our research, or minimize actually. You can see it, the result on the picture on the top right. The shiny part is a metal reactor, so that's what's there, that's what's supposed to be there. And then this black deposit on the inside of the reactor, that's called coke. So it's nothing more than carbon, it's what's in your pencil that you use to draw. But what it does to the process is that it prevents heat transfer because it acts as an insulator. It also increases pressure drop because there's less area for the gas to flow through. That means that it will be faster, so there will be a higher pressure drop. And it also damages the reactor material because the carbon that is there can diffuse inside the metal and change its properties and actually make it less resistant to strain And you actually have the risk of tube damage. So what you see in the middle picture is a tube that was being broken by the coke that was there. There's this one equation there in the middle, and the T internal is the one that's highlighted. That's because this process is very, very dependent on temperature. Even a difference in 10 degrees in interface temperature can increase the rate of coke formation by a factor of 2. So this temperature control on the inner on the boundary layer between the gas and the coke, or the gas and the reactor in a wall, that's actually what we want to focus on, and we want to get that one as low as possible. And for that, several techniques are available, and the one that we'll focus on here is this 3D reactor technology. So people have looked at different ways how they can decrease this temperature by increasing the heat transfer coefficient. So you want to get the heat in as efficiently as possible, so that your temperature difference between the hot surface and the process gas can be as low as possible. This is one of the slides that was made by my professor, and again to indicate that CFD can work together with reduced chemistry and finite rate chemistry, all based on HPC applications, to make the engineer of the 21st century. I've said this, now he will be happy. To come back to this, to these 3D reactors, actually I just want to give you a brief highlight of all the technologies that have been made. And we've actually simulated most of those, except for the IHT, but we simulated most of those based on tier 2 resources, so that's actually quite relatively small simulations. We apply, actually what we do in this, I will in the meantime show the results. What we would do is only not simulate the full reactor, because these reactors are sometimes 10 to 20, 30 meters long. We actually simulate a small part of the reactor, 5 centimeters, 10 centimeters, depending on how repetitive your pattern is. And by simulating this 10 centimeters and tracking it through the reactor, we can reconstruct what happens at every point without having to simulate the complete reactor. So that gets us speed-ups of up to a factor 100. So things that would not be feasible or would take an incredible amount of time are now feasible, and we can do routinely based on this periodic approach that we call it. Just to have a look at the results, we have the straight and the rifled fins. What you dare do is just increase surface area. So you have the heat transfer that's dependent on the difference in temperature, the surface area, and heat transfer coefficient. So the more area you have for heat transfer, the more power you can get in your tube. So that's like the basics of this straight and rifled fin technology. And as you can see, it has been applied, or has been, there's the earliest signs of it are in the late 1980s. And this is actually a technology that's pretty routinely applied in industry as well. What is newer is the technology which is called MERT, and then its variations SLIT MERT and X-MERT. It's a bit more recent, and it's there you have a very minor introduction, so it's not surface area, but there you want to induce secondary flows. In particular, there's like rotational motion inside your tube, so you have the gas which is flowing straight, and instead of just having parallel streamlines, you want them to rotate, so that's an extra velocity which will increase the heat transfer, and it will impact on the small rib that is there, and it will be forced to go to mix with actually the bulk and the bulk fluid inside the tube. So it's a way of breaking your boundary layers. The thing that you see on the simulation is temperature, so you see it's LES simulations. So you see just before the rib, the heat transfer coefficient is lower, so there your temperature increases, but behind the rib, there you see that the temperature is higher, is lower because your heat transfer is more efficient. IHT are discontinuous inserts, so we have not simulated those. We focus mainly on continuous technology, and the swirl flow tube is the last one. That's a recent invention by a Dutch licensor. They invented, instead of modifying the inner surface of the tube, they just changed the tube itself completely. So it's not a straight tube, but the whole tube is rotating. It's very difficult to make, and people are not convinced of the structural integrity yet. So there's a lot of research still going on how this will behave on the long term in a furnace. But the results are extremely promising based on our simulations. Actually, most of this work has been done by David van Kouwenberg, who could not be here today. He's about to defend his PhD, but that was his research for the past 4 years. And he invented this very nice analogy, because all the information that we have, actually the Italians knew already, because they designed it past us. presumably for optimized heat transfer, but in any case they were aware of this technology way before us already. That's another thing, actually, another part of David's work. So he not only focused on the reactors, but he also focused on what happens outside of the reactors in the furnace. So what you can see here, I'm sorry I cannot show any more details than this, but this gives you at least an overview of what happens in the furnace. So this is part of these are the complex burners, and what comes out is the flames, and that's an isosurface of CO concentration colored by, in this case, velocity, I think. So this is a way to visualize the flame structures in the furnace, and you can see that they're nicely close to the wall. It's what you want, because if you have flames impacting your reactors directly, then temperatures would be too high and you would actually melt the reactors that are inside. This is the reactor, so you have 5 inlet coils coming together and then going out again. They're colored by temperature, so that's more or less an indication of the information that we can get on just preliminary post-processing. Of course, we look at a lot more details, like where does NOx formation happen, so can we prevent harmful emissions, what are there ways that we can reduce soot formation. This is the next step that we can take based on these simulations. A last thing that was done by Laurien mostly, and also Jens is working on this now, is how we can look at the behavior of the reactor over time. Because I showed you the scope formation. In the beginning there's no coke, but over a period of time, which can be about anywhere between a week and about 50 days, the scope builds up until it reaches a certain point that the reactor cannot be used again. And what you can do to remove it is just burn it off. So stop the flow, send air through your reactor, and then you have carbon reacting with oxygen, and you just burn everything into CO2, and then your reactor is, we call it start of run condition. So you're with just your metal surface. But to see how this reactor evolves over time, we have to do these dynamic run length simulations. So it's not completely dynamic. We don't. Our time step is relatively big. We consider this coke process to be, or the rate of coke formation to be constant over a period of time of, for example, 12 hours. So every 12 hours we take a step, we see how much coke is deposited, and we add this layer dynamically based on dynamic meshing. And then we take several time steps until we reach one of the stopping conditions. So if one of the process conditions reaches its maximum tolerance. And then we did this for a quite simple reactor, so it's only a 10 meter straight reactor. But we did it for different internal geometries. So on the right you can see the bear, one of these fins, and then the C-rib, which is supposed to be like MERT. And then you see over time that their behavior is completely different. And then you can, this is actually a way to predict run length simulations, and it's something that industry is desperately looking for, because normally now they just put it in and see, but this is not the way actually that they want to operate their furnaces. They tend to look for a bit more detailed information. This is something that we have done on Tier 1, just because of the amount of time that it takes. This approach I was telling you about, this periodic approach, we cannot apply it in this case, because coke is not periodic. It will build up at different heights on different places in the reactor, so we cannot apply periodic approach. So this is a 10 meter long reactor that we simulated completely in several phases with detailed kinetics. So that was we spent quite some calculation time on this. And this is one of the biggest simulations that we have done so far. That was the application part. Now I promised you a second part also on a bit more the technical part of OpenFOAM. This is information that we gathered from the experience of using the resources for the last overall 6 years. Me myself only 3, but the information that was passed on from generation to generation. And we have been using Tier 2 resources for 6 years, and I think our first Tier 1 usage was 4 years ago, and we have had continuous projects ever since. What I want to start off is just a hardware overview. Sounds pretty basic, but it gives you an idea of what the difference is and what the potential benefits would be to use Tier 1. Just a quick show of hands. Is there anyone who has already used Tier 1? Yeah, okay, the minority, so I'm glad that I can at least tell something new for some of you. I compare it to the newest tier 2 clusters, so Golat and Swallowed. If you look at number of nodes, for a start, you can see just the size of the machine is a huge benefit. So you have about twice as many cores, or more than twice as many cores now in the new Brainiac machine. FYI, I show MUC, but that's the old one, so that machine is not active anymore. But just as a reference, the information is still there. If you compare now Golat with Brainiac, you have about about 3 times the amount of nodes and also a bit more cores per node. So the amount of cores in the machine is just 3 orders of 3 times larger. Memory requirements. I don't know. I assume we never face memory issues because we parallelize over sufficient amount of cores. I think in most of these cases it will be similar. So even the 64 gigabyte in Golat is sufficient. You have 128 in Brainiac, and even fat nodes with 256 for memory-intensive jobs. The thing that I want to stress is the interconnect, because I will show you some scaling data later. But what we saw was that cases that wouldn't scale on MUC with FDR InfiniBand or on Golat with FDR 10 would scale perfectly on Brainiac, and that's the advantage of the EDR. This is very expensive hardware, but the HPC or Flemish Supercomputer Center decided to invest in it. But the results are there. It's a clear advantage of EDR over FDR. So it reduces the incentive for the user to look at scaling because it would just scale automatically. But it's really nice as a user to be able to parallelize your cases that easily on the infrastructure. The only downside of Tier 1, it's not open and free like the HPC resources of Ghent University. It's project based, but it is free. So FWO since the beginning of 2016 pays for all the costs related to Tier 1 machine. Before there was a small fee for the users, but that has been changed since the beginning of 2016. Just to give you an idea of how much it costs, there's one number that I have in mind. The MUC machine that was actually, the hardware is still next door, but it's turned off. And the reason for that was that just the electricity to run it for a year costs 400,000 euros. So that's a cost that is now that FWO gladly pays for Brainiac, but that's just this number alone on electricity is quite staggering. That's why it's quite surprising also that they can make it free. This project based, I say it's a downside, but it's not something that has to prevent you from trying to use it. The application procedure is actually pretty straightforward. There was an information session about a week ago on Tier 1 proposals. So there's a lot of information out there on how to write it. The proposal itself also, it's a single document, it's 17 pages. It doesn't focus on the scientific aspect, it mostly focuses on the technical aspect. Is your code suited to run on this machine? Do you actually need that much resources? What's your justification for wanting to use Tier 1? And then some technical details about what the code does at scale and everything. There's 3 cutoff dates every year, so there's 3 moments that you can submit that proposals are discussed. The next deadline is October 2nd, so that gives you a perfect 3 weeks to start writing your proposal in case you want to switch. If not, there's a possibility to request a starting run, so that's a continuous call. It's an even simpler application procedure, and then you get 100 node days, and you can test your software, try it out, see if it makes a difference for you. It's like a stepping stone towards an actual full project. And like I said, FWO bears all the costs, so you have a limited amount of node days, but you don't have to pay anything for it. The machine actually is pretty similar to the UGent Tier 2 machines. So you have the same modules system, they're installed in the same way using EasyBuild. The scheduler is the same. The job scripts that you have to submit are the same, so they also use the same PBS scheduler. You can basically just transfer your case from one cluster to the other and run it straightforwardly. The only thing that you have to add is one line that tells you in which project they are calculating. So it's just this extra administration of the job, but that's once you have this line in place, it's very straightforward. And also not unimportant, there's the connection between KU Leuven, where the new machine is, and UGent happens via Belnet, which is a Belgian research network. It's a dedicated FiberNet connection, so you have a 1 gigabit connection. So even for large chunks of data that you have to transfer from side to side, for example, pre or post processing, there's sufficient bandwidth in place that you don't have to wait forever for your case to arrive. For more information, I put the hyperlink in there. You will have the slides. So that's the landing page for Tier 1. All the information is there. I promised you scaling data, so here it is. This is, of course, this is for cases that we are doing. So for these tubular reactors, the first cases that I have was one on MUC with about 8 million cells. Another one on Brainiac with the same amount of cells. And then there's a bigger case on Brainiac with about 40 million cells. What I want to stress, everything was done with OpenFOAM 2.0 with different versions of MPI, but that was what was available at that time. The conclusion, what I also highlighted, was that the scaling on MUC is better. Scaling on Brainiac is better than it was on MUC, just because of the InfiniBond. So the interconnection is faster. So actually the wall clock time is lower, and you can maintain your efficiency. Just because your MPI interconnects, the MPI statements can be passed on quicker, and there's no bottleneck in the bandwidth. Actually, what is the bottleneck in these cases? If you have 40 million cells, for us at least, it's pre and post processing, just to be able to open the case and visualize anything that we want. So pre and post processing is we transferred from computational resources to run the case being the bottleneck to actually the visualization and the processing of the results. So that's why we were very happy that the Tier 1 in Leuven, their specialty is by the way GPU acceleration. So they in one of the login nodes of the machine, they installed now a GPU, and you can do remote visualization with no machine client. I haven't tried it yet, but I will. It's something that they will have done during the latest maintenance, so that was 2 or 3 months ago. In the afternoon there will be a session on VNC visualization, which is, I know machine and VNC are very similar, or I don't know about technical similarities, but their usage is the same, their purpose is the same. So VNC is available on all Tier 2 machines, Tier 1 as well. So that's a way to visualize remotely directly on the cluster where you run your simulations. The number of cores is different also in MUC and in Brainiac. So now I show the scaling in number of cores. So then you can see that the speed up even on a larger number of cores, up to 900 cores. For the biggest case, it's acceptable. So which was we were very happy with these results. That's same data but visualized. This is only Brainiac simulation, so even for the smaller case with only about 800,000 cells, scaling is pretty well, and you even exhibit superlinear scalability, so the efficiency goes up if you go to more cores, which is explained typically with Kasha effects. So you have this very fast memory close to the processor, so if you use more cores you have more of this fast memory available, so a larger part of your case can be accessed quicker by the processor. What I want to stress, just putting it out there, the choice of decomposition method that you use is actually quite important. We have complex cases, so we cannot. I was in the first presentation. We saw that this linear decomposition was the most suited in that case. I was really happy to see that indeed. The scaling was so much dependent on how you decompose it. I saw that you used Métis for the decomposition. It's a default also in Fluent, but the default in OpenFOAM is Scotch, so we have used mostly Scotch, and sometimes simple if you know how to do it straightforwardly. but we MULTIS is a very interesting alternative. One thing that I wanted to highlight as well is preserve patches for periodic cases. So that's what we want to do if you want to recycle information from one patch to the other. This is inherently a transfer of information, so it's most efficient if these two patches are treated on the same processor. And then you limit the communication in between. So this preserve patches, it's in the decomposed direct dictionary that you can put that as a keyword. And you can specify that certain patches should be treated on the same processor. This is now just a quick follow-up of a couple of best practices. If you use third-party measures, so if you use OpenFOAM native measures, block mesh, snappy hex mesh, foamy hex mesh, the OpenFOAM automatically makes sure that the numbering of the cells is done in the most optimal way. So the numbering of the cells will also then determine how it's decomposed. So block mesh and snappy hex meshes typically scale really well. If you use third-party measures, that might be a problem. For complex geometries, we use pointwise, and then we see that pointwise meshes, even if they're exactly the same or as close as possible to things that we generated with, for example, Snappy, that they don't scale as well if you don't use this renumber mesh utility. So they just change the orders of the numbering of the cells, but it makes quite a big difference in bandwidth and speed if you want to use third-party meshes with OpenFOAM. Also, the OpenFOAM version that you use, and in particular the compiler toolchain, is important. This is a screenshot that I made last week for Tier 2, where you see that now the default one on CO7 is this OpenFOAM 4.1 installed with the Intel 2017 toolchain. So then you make use of the latest developments in compiler technology, so you use your processor optimally, the latest version of the MPI libraries. So it makes quite a difference in performance compared to older versions. For example, this was the one that we started with 3 years ago. It's very nice of HPC to still offer it, and sometimes for compatibility reasons we still go back to it, but it's not good practice. So we should rewrite. And just for your information, I also put there what's there on Tier 1B. So you see that there's a lot of versions as well, and then everything is compiled still with the 2016. So there they have only one compiler toolchain. A bit about checkpointing. So how frequently do you write out your data? It's also a very important point to consider. This is an example of a control dict library that I found just on the OpenFOAM the GitHub repository, where you can see that the write interval is pretty high. They don't use purge write and they don't use write compression. That's actually the 3 things that you can change to optimize your I/O. That's just the guidelines that we use. Writing out every 2 to 3 hours for a 72-hour job is sufficient. So also the number of times that you keep, it's not necessary to keep all these points, and that's of course you do transient cases, but OpenFOAM allows you to keep only the last 2 or 3 times that it wrote out. So once you write a new one, the old one will be purged. And then for big cases, this compression is really nice, because if you compress it OpenFOAM does it automatically. You can still use the same pre and post processing. It saves you time in transferring the cases back and forth. And it also reduces your disk space to about 1/3 of what it was. So this optimized can look something like this. Locations where you run your job is also important. There's some locations that are available for the Tier 2 resources, both on Tier 2 and Tier 1. One is VSC data, but these are slower disks. So this is meant for long-term storage. So if you each time have to write out a lot of files to this location, it will be slow. So that's why you have the Scratch, which is on 15K disks. So they are a lot faster, and they're actually meant for continuous I/O. There is also the VSC Scratch node, which is a disk which is located on the compute node itself. So that's actually the fastest connection that you can have between the disk and the processor. But that's suited for single node jobs. So if you're limited to for example 28 processors on Tier 1, and it's accessible. It's a temporary directory, so if your job ends, you have to make sure that your data is copied again to a centrally accessible location. But that's a good alternative if you have to do a lot of small cases and you need a lot of I/O. One thing that I saw when researching for this presentation, the statement runtime modifiable. It's something that's in control dict, it allows you to change the files at runtime. So every time OpenFOAM checks at the beginning of a new time step, has the file have the files in system and in control. System and in constant. Have they changed? And if so, I will apply the changes in the next time steps. Okay. Before I go deeper to that, I want to refer to best practices document, but that's something that Kenneth will show this afternoon. One thing that's new also in OpenFOAM 5 that was brought out in July is a collated file format. So as you know, OpenFOAM in every time directory you have one file per field that you want to save. OpenFOAM has programmed a new, at least the openfoam.org branch, has a new format, a file format, which is called collated. And as you can read, the data for each of the decomposed fields is collated into a single file. So you still have each folder per time step, but per time step all your information is in one single file. It's way easier to handle for shared file systems. And instead of having a lot of very small files, you have one big file that is there anyway. The advantage is as well that it can be threaded, which means that your simulation can keep running while the master processor is writing out the file. Now, every time it's writing, you have to wait, so the CPUs are idling. But this allows you for one CPU to process all the I/O, and for the others to keep calculating on your case. It's new on OpenFOAM 5, and which will be installed soon on Tier 2 resources. So please feel free to use it. It's just a couple of keywords in control dict, so it shouldn't be too. From what I've seen, it shouldn't be too hard to actually start using it. This is now I switch back to this runtime modifiable. It's two slides that I want to show you. It's not cases that I've run, but cases that I've seen in the framework of Praise. So the tier 0 system where they wanted to check whether OpenFOAM can scale on really to 10,000, 100,000 cores. It was done on Curie, which is a tier 0 machine in France. The number that I want to focus you on is stat call. So that's a call that OpenFOAM does to check whether the time of modification of a file is more recent than the time when the last time step has started. So that's the way that it uses to check to actually implement the runtime modifiable option. So that's what they have been done. That's what they saw when they were benchmarking it. That there's a lot of calls to this routine, and it results in pretty high compute times, as you can see in the top row. If you focus on this row that's now highlighted in red, you can see that if you stop this runtime modifiable, that this number of stat calls decrease by a factor 100. And I don't know if you remember the compute time, but it's also a factor 2 and just in wall time from this runtime modifiable. I have to mention that this was done in OpenFOAM 1.7, and I haven't reproduced this, so I'm hoping that in more recent versions of OpenFOAM this was changed and this is done more efficiently. But it's something for sure to look into, to consider when you're running on HPC. This is my last slide. I don't want to say my last content slide. There is a project running at Ghent University which is called Prediction of Turbulent Reactive Flows, with a very nice acronym PRETREF. I've put the website and the contact person there because it's a framework that we are sharing information on OpenFOAM best practices on. The groups that are involved are Biomat, ID Lab, FlowHecom, and also the LCT. But the coordinator is done by the Flow, Heat and Combustion department. The areas that we are focusing on is reduced chemistry, which is our job, and then spray combustion, unsteady sprays, and fire dynamics. Just for your information, the website is there. The GitHub repository will be public soon. So that's where we'll gather all our solvers, utilities that we wrote for our cases. With that being said, I want to thank the colleagues at the LCT and of course the Flemish Supercomputer Center and the UGent HPC Center. And I will gladly take any questions if there are any, and if there's time. Thank you.
Any questions for Pieter?
When should you execute renumber mesh? Before decomposing the case or after decomposing?
There's an option to do both. Yeah, so renumber mesh, it's very consistent. So of course, if you have your initial fields already, renumber mesh knows how to that also has to renumber the fields, but it can work both on non-decomposed as well as decomposed cases. But the easiest way is just when you have the when you load the mesh, when you transfer the mesh to OpenFOAM format, then apply renumber mesh, and then all your initial conditions will just be constant values. So before running any pre-processing tools that you have to develop your initial conditions, you can run the renumber mesh utility once, and then the information is only in one place, and the numbering information, and then all the fields will be based on the renumbered mesh.
More questions? Okay, thank you, Pieter.
Thanks.